So in class previously, we've learned all about how to draw LOL diagrams, and now we're going to put that learning into good use because we're going to actually use it to solve a problem. We're going to go through problem number 1 on worksheet number 3 in order to do that. So as you see in those instructions on worksheet number 3, for each problem or question, we want to draw an LOL diagram, and then we're going to use that LOL diagram to determine our unknown quantity, or quantities. In some cases, you might be doing multiple. We can also assume air resistance is negligible unless it's otherwise stated. In our first problem here, we have a block that is initially moving to the right at 5 meters per second, and then it compresses a spring, and that spring causes it to stop. So that first thing we'll do is draw that LOL diagram, starting out with our L, our O, and our L. And I always label my diagram here kinetic energy, gravitational potential energy, and elastic potential energy. If you are in regular physics, we use a KE for kinetic energy. We use PE sub G and PE sub S. So whichever of those two symbols you are accustomed to is totally fine. And then we'll do our final as well. And of course, including that change in thermal energy in our final L there. And once we have our setup for our LOL diagram, it's our time to go ahead and add things to our system. So in this case, we have a block, and that block ends up interacting with a spring. We know we always have the earth in our system, and I'm going to go ahead and put the ground in our system as well. Our next task, the one that is most commonly forgotten, but we want to make sure that we don't forget it, is defining our reference level. In this case, I'm going to choose the reference level to be the floor, and I'm just going to mark it on my diagram right here. So determining how much energy or what types of energy I have initially, I know that it's moving, and therefore I know that we're going to have kinetic energy. I know that it's at the reference level, so I'm not going to have any gravitational potential energy. And in my initial scenario, my spring is not being compressed, so I have no elastic potential energy. So all my energy starts out as kinetic energy. In my final scenario, it is not moving, so no kinetic energy. I'm still at the reference level, so no gravitational potential energy. This time I do have a spring that is compressed, so I know that I'm going to have elastic potential energy. And the problem specifically says to assume that none of the initial energy ends up stored as thermal energy, so there's no change in thermal energy. Since I have nothing outside of my system exerting a force on my system, that initial kinetic energy that I had is going to be equal to that final elastic potential energy that I had. And we know that that's the next step in our problem here, is to write out our equation. So K initial equals US final, or again, if you're in regular physics, our equation would be KE initial equals PES final. Just using those slightly different symbols to be consistent with our textbook there. That's everything that we've done so far. That's review. So now we're taking it one step further by using the equations for kinetic and elastic potential energy. So we know that kinetic energy is 1/2 mv squared, and the velocity is what is our initial here, because our mass isn't changing. In our final scenario, we have elastic potential energy, or 1/2 kx final squared. So I'm just taking those equations that we've learned previously and plugging them in for my quantities here. Looking at the information given to me, I know the mass based on my diagram is 8 kilograms. I know the initial velocity is 5 meters per second, and I know the spring constant on my spring. So I know everything other than the spring compression, that x, and that's what I'm looking for in the problem. So I can now plug some numbers in. That mass is 8 kilograms. That initial velocity is 5 meters per second. Don't forget to square that initial velocity. and my spring constant is 50 newtons per meter. And so we can use that to calculate our final quantity here. And I'm stuck without a calculator right now, so hold on one moment. Okay, so plugging those numbers into a calculator, I end up getting that X final is 2 meters. So that spring compresses 2 meters in bringing my object to rest. In many of our scenarios, our problem will tell us what our initial and what our final is. But there are times when we won't be told that. For example, in question number 3, we've got this pig standing on top of this muddy hill, and the problem, specifically the diagram, it doesn't show me where the initial and where the final is. So that's something you might need to decide. In those cases, my suggestion is to look at the information that you're given and figure out 2 points where you know information. So for example, it tells me that the hill is 100 meters long and there's a vertical drop of 30 meters. So I know when he's at the top of the hill, he's 30 meters above the ground. And it's asking for the pig's speed at the bottom of the hill. So there's 2 locations kind of indicated in this problem. One of those locations is the bottom of the hill, and the other one is the top of the hill. And so I would consider the top of the hill to be my initial and the bottom of the hill to be my final. So now your task is to take what we've learned in this video and put it into practice.